Okay, so we're going to work on practice exam 2 here, and we're going to do it all together. And so let's start with the first one. We're going to work it through. What is the probability of reaching into the box and randomly drawing the chip number 301? Let me start at the beginning. There are 309 identical plastic chips numbered 1 through 309. What is the probability of reaching into the box and drawing number 301? Express your answer as a fraction or blah, blah, blah. Okay, so what we're interested here is in the number of results or the number of outcomes that we want, that we are interested in, over the total possibilities. So this is nothing more than the total possibilities. So this is 1 through 100 to 309. So what are the total possibilities of drawing one chip? It's 309 possibilities. And which one are we interested in? We are interested in just 301. So this is one possibility out of the 301. And if we turn that into a decimal, 1 divided by 309 is equal to 0.0032, and there's your answer right there. All right, well, that one's easy enough. Let's move on to the next one. A standard 6-sided die is rolled. What is the probability of rolling a number less than 4? All right, so we did one of these in class, and we need to stop and, maybe I can do it with a thinner. Can I change the thickness of this thing real quick? Let me go to that. We have 6 possibilities when you roll a 6-sided die, right? We have 1, 2, 3, 4, 5, and 6. And here it's asking you for less than 4. So this is the probability that x is going to be less than 4. And what is that? That probability does not include the number 4. It includes only those numbers that are less than 4. So it includes these probabilities. It includes the 1, the 2, and the 3. All right? So same thing, total number of possibilities that we are interested in on top, and the total. These are the ones that we have of interest, and these are the total on the bottom. So we are interested in 1, 2, 3 out of the 6. And there are 6 total possibilities because it's a 6-sided die. Therefore, it is 1/2, which is also equal to 0.5. And there's your answer. Okay, so where were we? Let's move on to number 3. Number 3. Let's get some space in here. You decide, there we are. You decide to record the hair colors of people leaving a lecture at your school. What is the probability that the next person who leaves the lecture will have red hair? Express your answer as a simplified fraction or decimal rounded to 4 decimal places. Okay, so you may be tempted to look at this as a binomial because you're looking at whether somebody is red hair or doesn't have red hair, but that's not really what we're asking. What we're asking is what is the probability of drawing this one red hair coming out of the room? And so this is like a marble question, all right? There are all these people in the room. Here's our room, and there's all these people in it, and they're going to come out one by one. If they come all out at random, one of them's going to have red hair, right? So what I want to do is look at the same thing we did before, items of interest over the total possibilities. All right, so what are the items of interest? That's easy. It's the 20. All right, so that's 20, and that goes on top. So what are the total possibilities? The total possibilities are all of these guys put together. 20 plus 20 is 40, and that's plus 43 is 83, plus 38 is 121, plus 34 is 155. So we have 20 over 155, and that reduces to 155 divided by 5, or 20 divided by 155 is equal to 12.9, or get out of there, or 0.12 290. If you wanted to reduce this, you could reduce these both by 5, and you end up with 4 over whatever 155 is divided by 5 over 31. All right. Okay, so not a whole lot of challenges here. Let's go to the next one. Let's make some space so we can work. A coin is tossed 6 times. What is the probability of getting at least one head? Express your answer as a fraction or decimal rounded to the next 4 places. Okay, so here you can use a little multiplication. You can use the binomial, but let's just use simple multiplication here. So if I toss the coin 1 time, I get 2 possible results, right? The head and the tails. If I reduce it a 2nd time, then I can get heads or tails, having done this one and that one, and the same thing for that one, heads or tails, and so on. So this guy is 2 possibilities, and that's going to multiply it by 2 possibilities times 2 possibilities, and so on. But that's going to be kind of contentious. So what we're going to do is we're going to take the total possibilities by 2, and we're going to take it to the 6th power, and 2 to the 6th, and I'm actually going to use a calculator here. Where is it? 2 to the x. And that's a total of 64. And that's my phone. All right, I'm back. So I've erased some of this other stuff to give us some space, but this 64 represents the total possibilities. Total possibilities. So we're going to come, let's put it over here in the bottom. So this is over here in the corner. So that represents the 64 total possibilities that we can get after flipping a coin. But now we're going to look at this question and say that it has at least one head. Well, there's an intuitive solution here, but before we get there, let's talk about all the possibilities, right? The possibilities of x. You can get 0 heads. That's the one that people are going to forget. 0 heads, 1 head, 2 head, 3 heads, 4 heads, 5 heads, or 6 heads. And what does this guy at least 1 mean? It means I have to include the 1, and I can get any of these. This is what I'm interested in, right? This is the stuff of interest. This is my interesting stuff. This is the solution. But then I also have this, guy, and this is not the one I want, okay? And this is where the intuitive solution comes from. So let's think this through for a second. Well, if I have 1, 2, 3, 4, 5, 6 flips, 1, 2, 3, 4, 5, 6, I can have tails, 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 and then all the other combinations, tails, 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 heads, all the way down to, we'll put 3 dots, heads, 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 heads. Now, intuitively, only one of these, you can sit down and add these up. All the possibilities where there's a 1 heads, and the next one when there's 2 heads, and the next one when there's 3 heads, and you add them all up, or you can look at this knot, okay? And we can look at the probability. We can look at the probability that x is at least, which means greater than or equal to 1, and its complement is equal to the 1 minus the probability that x is equal to 0. Does that make sense? This makes it a whole lot easier to calculate this problem because there's only 1 0. And there's only one combination where I don't get a heads, and that's this guy right here. The very, very first one, when they're all tails. So how many different possibilities exist where I don't get a heads? Well, just the 1. And is that our answer? No, it isn't. Don't forget that I am interested in at least 1 head. So I'm interested in all these blue ones. Okay, this is not correct. Okay, I want 1 minus, sorry, let me put it over here. I want 1 minus the probability that x is equal to 0. What is the probability that x is equal to 0? Well, I can calculate that over here on the side. Let's say the probability that x is equal to 0 is only 1 possible solution out of the 64. So what's 1 minus that? Well, that's 64 over 64 minus 1 over 64, and that gives me back to blue, 63 over 64. And the percentage of that is equal to 0.9844. Okay, this is a complement question, and it does require a little bit of intuitive thought. Okay, but I would, if I was in your shoes, when you have something like this, take the time to draw out this table over here. It can be very, very, that's supposed to be an arrow. That can be very, very beneficial. Okay, so this one is not intended to be confusing, but it can be. A card is drawn from a standard deck of 52 playing cards. What is the probability the card will be a diamond and not a face card? So we're looking for the probability that the card is a diamond and the probability that it is not a face card. Well, don't confuse these. Don't add these together. Be very careful because we're dealing out of the 52. We got to keep things in perspective here. What we're doing here is putting that guy on the inside. Get out of there. Get out. Erase already. Thank you. That it is a diamond and not a face card. All right. So first of all, let's build our ratio. There's 52 total cards. So there's 52 on the bottom. All right, easy. So how many diamonds are there? There are, that's a diamond, the ace, the 1, the 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10, the jack, let me scroll down a little bit so you can see the rest of it. The jack, the queen, and the king. Now, this is an ace. Now, how many of these are not face cards? Well, the jack, the king, and the queen are face cards, so they got to go. Gone, gone, gone. So we end up with a total of 1, 2, 3, 4, 5, 6. Wait. I counted this guy twice because the ace is our 1. So this is going to be the ace, right? Okay. Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 are the total that I'm interested in. That guy goes on top. We have 10 out of 52. Which is the same as 5 out of 26. That's our answer. And that reduces to a decimal of 0.1923. Easy cheesy. So number 6. Let me reorganize this so it makes more sense. I'll put that over there. All right. Determine whether the following events are mutually exclusive. Choose a student who is a French major or a business major from a nearby university to participate in a study. Assume that every student only has one major. That one major is key, right? So we have the French major or a business major. And the real question here is, can you be both? Can you be both a French major and a business major? In the real world, you can, but here it's telling us to assume that each student only has one major. You can't be both. Therefore, these are mutually exclusive. You can either be one or the other. You can't be both. That's number 6. Number 7, Ms. Fraga's history class has 109 students classified by year and gender as illustrated in the table. There's our table. Males, females, freshman, sophomore, junior, senior. Ms. Fraga randomly chooses one student to collect yesterday's work. So we're looking for one student out of the 109. All right, that makes sense. What is the well, let's hold on a second. Let me make space in the right place. Number 1, what is the probability that she selects a female given that she chooses randomly from only the sophomores? All right, well, in this case, we are interested in these guys. Do I have a highlighter? I think I can just highlight the whole thing, right? I'm only interested in the sophomores. Okay, so what is the total number of sophomores? Remember the original still applies here. Student green. So the original question still applies. Let me erase this. It's the number of results that we are interested in over the total possibilities. So what are the possibilities? Well, the possibilities are only sophomores. So I'm going to add these together and get 21. So my denominator is 21. And what are the possibilities? That she's going to pick a female, given that she chooses only from the sophomores. Well, how many females are there? There's 5 females. That's 5 out of 21, and that becomes 0.2381. So almost a 25% chance, 2381. All right, well, that's easy enough. Step 2, let me get them closer together so we can, step 2. Let's get some space over here. What is the probability that she selects a sophomore given that she chooses a female? Well, in this case, we're going to go the other way. We're going to go south. So our population here is the females. So I'm going to add up all these females. 18 plus 5 is 23, and 9 is 32, and 16 is 48. So there's 48 total females. Remember, she's going to choose a female first. And only from the females is she going to pick a sophomore. Well, how many sophomores are there? It happens to be the same number we calculated before. There's 5 sophomores. So there are a total of 48 possible choices because it's only the females. And then she's going to, what are the odds then of picking a sophomore? The sophomores are on top. This is sophomores over, or I should say female sophomores over total females. And that's 5 out of 48, which is equal to 0.1042. Easy cheesy. Evaluate the following expression. This is a traditional factorial. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 5 times 4 is equal to 20, times 3 times 2 is equal to 6, times 1 is equal to 1, so that's 20 times 6. You guys see what I did there? I did these guys and put them together, and then I multiplied these guys and put them together, and that equals to 120. 120. I hope your handwriting is better than mine. A coin is tossed 7 times. How many different outcomes are there? Well, the coin has 2 outcomes, right? It has a set of either heads or tails, tails or heads. So it's 2 possible outcomes every time. And we kind of did one of these before. So how many different times does he toss? It tosses 7 times. That's 2 to the 7. If you don't know how to do this one, there should be an X to the Y button on your calculator, and so you're going to hit 2 X to the Y. This is one button, X to the Y, and then 7. That's how you get the little there, and that should equal to 128. 128. Excellent. Evaluate the following expression. Combinations. This doesn't need to get out of hand here. Remember that our expressions for NCK is equal to n factorial over n minus k factorial. Remember where the parentheses are, times k factorial. And so here we're just going to plug and play the 9 where the n is equal to 9 and the where's my erase button? Somebody's moving my pen. And the k is equal to 5. And then we're just going to plug it in. So this is going to be 9 factorial over 9 minus 5 factorial. This is inside the parentheses, so we're going to do it first. 5 factorial, okay? So this is going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 9 minus 5 is equal to 4. So that's 4 times 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. Now you'll notice that these guys will cancel out these guys, and I end up with, making more space, and I end up with 9 times 8 times 7 times 6 over 4 times 3 times 2 times 1. Now you can multiply these out and then erase them and then whatever, but there's a simple, an easier way to do this is to turn around and say, hey, look, the 4 and the 2 multiply together into an 8. So I'm going to cancel the 8 and then those two because those are the same. And then I have the, what else divides by 3? Oh, there's a 9 and a 3. The 1 just kind of disappears. 9 divided by 3, that one goes down and this one goes to 3. That one becomes a 3. So I have 3 times 7 times 6. That's a lot easier to calculate, isn't it? And then we have 3 times 6 times 7, and that equals to 126. Number 11. There are 12 people in an office with 6 different phone lines. If all the lines begin to ring at once, how many groups of 6 people can answer these lines? Okay, so this is a combination permutation question. And the real question is this a permutation or a combination? Which one is it? So what's the question that we ask when we have a permutation and a combination? We ask the question, does order matter? So does it matter that one person answers the phone first? Does Susie answer the phone first and then Ted and then Jack and then whatever? Or does it matter, or does it not matter who answers the phone? Well, of the 12 people, there are 6 lines. How many groups of 6 people can answer the phone lines? Well, it doesn't really matter. So this is a combination question. This is a combination. Order is not important. There are 12 different people, and we are trying to answer 6 different phones. And it's groups of 6. This is the 6 that I want. The fact that there are 6 phone lines means that 6 people can answer the phone, but that's not the question. It's not what the question is asking. The question is asking how many groups of 6 people can answer the phone. So that's 12 combination 6 based on this one. And I make a point of pointing that out because this could be 8, and the question says how many groups of 6. Well, it doesn't matter that there's 8 phones. What matters is that 6 people are answering. Okay? Take the time to make sure that you're reading the question right. This 12 combination 6. So just like we did before, this is going to be 12 factorial over 12 minus 6 parentheses factorial 6 factorial. And if I write that out, it's going to be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. Note that I go all the way to 6 and so on. Divided by 12 minus 6 is 6 factorial. So that's 6 times 5 times 4 times 3 times 2 times 1 times 6 factorial. 6 times 5. Note that this group is separate from that group. They're still going to get multiplied by each other, but it doesn't matter. 4 times 3 times so on. Okay, so same thing as we did before. We're going to look at this 6, and this 6, and I'm going to cancel that one, cancel that one, cancel that one, cancel that one, all the way across. All of that disappears. And we end up with this combination over here. And try to figure out where else we can do some combinations to make this easy. Well, 3 times 2 is 6. That's gone. That doesn't help me. 2 times 8. 2 times 4 equals to 8, so I can make that one disappear. 3 and 12, I can make the 12 smaller. I can do the 9 and the 3 again like we did before. So that becomes a 3. Let's do it in blue. That becomes a 3. 5 divided by 10. I can take the 5 out and divide the 5. And that becomes 2. And on very cleanly, I can take the 6 and the 12. Again, let me do it in red. I can take the 6 and the 12, and this guy becomes a 2 on top. So now I know this is messy. 2 times 11 times 2 times 3 times 7. And hopefully you followed me where we did the pairing here and a pairing there to try to make it easier. If you don't like any of this stuff, just multiply it all out and get some big number on top, and multiply it all out on the bottom and get some big number on the bottom. But this makes it easy to calculate. So this is 22. 3 times 2 is 6 times 7 is 42. So 22 times 42 is equal to 924. Okay, now if this was confusing up here, I could do 12 times 11 times 10 times 9 times 8 times 7. And the other one gets canceled over 6 times 5 times 4 times 3 times 2 times 1. And that's 12 times 11 times 10 times 9 times 8 times 7. And I get 55 440 on top, divided by 6 times 5 times 4 times 3 times 2 times 1, 720 on the bottom, and I should still get the 924. Number 12, the newly elected president needs to decide the remaining 3 spots available in the cabinet she is appointing. There are 15 eligible candidates where these positions, where rank matters. Rank matters. How many different ways can the members of the cabinet be appointed? Well, rank matters, which means that order matters. This is a permutation. Okay? So what is a permutation? NPK is equal to n factorial over n minus k factorial. And in some sense, this is a lot easier to calculate. So n is equal to 15 total candidates, and there are k spots remaining. That's 3, so this is going to be 15. Let me straighten it up. 15 factorial over n minus k, 3, 15 minus 3 factorial. And this is obviously 12. So this is equal to 15 times 14 times 13 times 12 times 11 times 10 and so on over 12 times 11 times 10 times so on. That set cancels that set, and we end up with 15 times 14 times 13, which is relatively easy to type into our calculator. And that gives us 2730. There are 2,730 different combinations or permutations eligible for the eligible candidates. Okay. Consider the following data. We have these x's, and we have these probabilities that they're going to occur. Note that these guys all add up to 1.0. Okay, we're stepping into a frequency distribution. First question is find the expected value, round your answer to 1 decimal place. Well, I really like to do this vertically, so I'm going to rewrite it over here on the side. 3 and 0.3, 4 and 0.1, 5 and 0.2, 6 and 0.2, 7 and 0.2. So this is nothing more than a weighted average. I'm going to multiply across the top x by the probability of x. I'm going to multiply, 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 and then I'm going to add them all together. So that's 3 times 0.3 is equal to 0.9, 0.4, 1.0, 1.2, and 1.4. If I add these together, I get 4, 2, 6, 0, 1, 19, carry the 1, 4.9 is my expected value of x, 4.9. Okay, let's make some space here. Oh, the variance. Okay, so the variance. So what we're going to do is do our variance equation, and here we're going to multiply by the probability of each x by the summation of, the summation goes on the outside. We're going to add up the summation. We're going to add up the probability of x times x bar minus x squared. All right. So let's keep this guy, because we know it's 4.9, over there. I should have made more space here. And let's go back and, you know what, let's just make some space here. Just make a bunch of space and we'll do it from scratch because that's the right thing to do. Okay, so we have x is 3, 4, 5, 6, 7, and the probability of these x's is 0.3, 0.1, 0.2, 0.2, and 0.2. And now I'm going to do x bar minus x. This is the inside here. So what's x bar? X bar is 4.9. So this is 4.9 minus all of these. So 4.9 minus 3 is 1.9. 4.9 minus 4 is 0.9. 4.9 minus 5 is negative 0.1. 4.9 minus 6 is negative 1.1. And this is negative 2.1. Okay. The next thing I need to do is square them. So 1.9 squared. Don't I have an easy squared button here? Apparently I do not. I have a cubed. There it is. Squared. 3.61. 0.9 squared is 0.81. 0.1 squared is 0.01. 1.1 or negative 1.1 squared is 1.21. And negative 2.1 squared is 4.41. So now we have to change things a little bit here. Because instead of adding these up like I do a traditional variance equation, I have to multiply this. I have to multiply this guy by this guy. And that guy and that guy, and that guy and that guy, and that guy and that guy. And you get the point. Okay, so 3.61 times 0.3 equals 1.083. And this is where the probability of the x times x bar minus x squared comes into play. But note that I haven't added them up yet, okay? 0.81 times 0.1 is 0.081. 0.2 times 0.01 is 0.02. 1.21 times 0.2 equals 2.42. And 4.41 times 0.2 over here times 0.2 equals 0.8. Wait. 0.882. This one's not right. Let's do this guy again. 1.21 times 0.2, 0.242. So this guy, the decimal's in the wrong place here. 0.242. And if I add all these guys up, I get 1.083 plus 0.081 plus 0.02 plus 0.242 plus 0.882 equals 2.308. 2.308. And this is where the summation comes in. So this is my variance. Excellent. Standard deviation. Wait, is that right? Yeah, 2.3. There it is, 2.3. All right. Standard deviation. Standard deviation is nothing more than the square root of the variance. We have the variance. Variance is equal to 2.3. So I'm going to just take the square root of 2.3. 2.3 square root. Where's my square root? 2.3 square root 1.51. 1.51. One decimal place, so 1.5 is the answer. 1.5. Find the value. Okay, great. So now, find the value of the probability x is greater than 2. All right, let's grab these guys. Let me grab this guy. And just copy this guy over. So we're not doing it over and over again. There we go. So let's find the probability that x is greater than 6. Well, what is the probability? Let's change colors. We haven't used some. Let's use something different. Let's use purple. See how that works out. What is the probability that x is greater than 6? Well, what is x greater than 6? I'm going to draw a line here. Do I include the 6? I do not include the 6. So it's whatever's on this side. The answer is 0.2 because it's just this one and this one alone. That's it. Easy cheesy. What is the probability? What is the probability that x is greater than or equal to 7? So here's 7. And because it says equal to 7, then I'm going to include the 7. And it's asking for everything that's bigger than that. So I draw my line in the same place. And the answer is still 0.2. It's still just only that one. Let's construct 14. Construct a discrete probability distribution from the random variable described. Express the probabilities as simplified fractions. The number of heads in 3 tosses of a coin. Ooh. Okay, let's think this one through real quick. So what's going to happen is I'm going to throw the coin 1, 2, 3 times. And in these combinations, I'm going to get either a heads or a tail, and a heads, and I'm going to throw it again. I'm going to get either heads and a tails, a head and a tail, and the same. 2 for that one, 2 for that one, 2 for that one, 2 for that one. So the easiest way to do this is, since there's not a lot of tosses here, don't get heavy into the math. Let's just do it writing out all the different combinations. Sometimes it's easier just to write them all out. So we have heads, 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 tails, heads, tails, heads, heads, tails, tails. I'm going to run out of space here. But that's okay. We can make more. Tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And now, let's erase this and let's find out what is it asking us. The number of heads. Well, what's the number of heads? 0. There's 1. Oh, no, sorry. 3. There's 3 heads here. 1, 2. There's 2 heads there. 1, 2. 2 heads there. 1 head there. 1, 2. 2 heads. 1 head. 1 head. 0 heads. And to do the frequency distribution, I'm going to count how many there are. So here's the 0. How many zeros do I have? I have 1 0. Just making a happy face because you guys are awesome. 1 0. I have 1, 2, 3 1s, 1, 2, 3 2s, and 1 3. Okay, so this is asking for the frequency of how often these are happening. And the question asks for simplified fractions. So this is 1 over 8 possibilities, 3 over 8 possibilities, 3 over 8 possibilities, 1 over 8. 1, 2, 3, 4, 5, 6, 7, 8, which is also going to be 2 to the third. 15. If you draw a card with a value of 4 or less from a standard deck of cards, you'll pay 173. If not, you pay me 48. Aces are high. All right, so we have 2, 3, 4, 5, 6, 7, and so on. 4 or less. So I draw my line here. Find the expected value of the proposition. All right, so this is plus 173, and this is, any of these are minus 48. So what are the odds of getting this? 2, 3, or 4? Well, that's going to be, what's the probability of winning is equal to, out of 52, is equal to the 2, the 3, and the 4, but there's 4 different suits, right? There's the diamond, and the heart, and the club, and the spade. This is terrible. And the spade. So that's going to be 3, 1, 2, 1, 2, 3 times 1, 2, 3, 4 different combinations. So that's 12 out of 52. So that is, what, 6 out of 26, 3 out of 13. What's the decimal for that? 3 divided by, or 3 times 13. 3 times, sorry. 3 divided by 13. I was right the first time. 0.23. So you have a 23% chance of winning. What's the probability of losing? Well, if this is 3 out of 13, you can do the same thing. We can count these 5, 6, 7, 8, 9, 10, king, queen, jack. But I can also get this 12 and say, well, what's 52 minus 12? That is equal to 40 out of 52, which is equal to 20 out of 26, or 10 out of 13, which is equal to a probability of 10 divided by 13, 70.76 or 77. Note that these two guys are complements of each other. So you could also just do 1 minus 0.23 and arrive at the same answer. Okay, so now we're going to combine this with our expected values. So the probability of winning is 0.23. And what do I get if I win? I get times $173. Or I have a 0.77 chance of losing. And if I lose, what do I get? I don't get anything. I have to pay, or negative $48. And so what we end up having here is nothing more than a simple weighted average. Okay. 173 times 0.23. This is my x. This is my probability of x. And negative 48 times 0.77. Let me close that out. And what does that equal to? So 173 times 0.23 equals 39.79. Or I have negative 48 times 0.77, and that equals to negative $, negative, actually it should be on the inside, negative 36.96. But there's a second part of the question up here. There's a second part of the question that asks, well, let's just move it because we can. I'll put it over here. Oh, I'm sorry. We didn't actually take the average, did we? We just kind of played with it. So now I have to add these together. And 39.79 minus 36.96 is equal to $2.83. This is my expected value. That might not make a lot of sense because if you look up here, the odds of winning are very low and the odds of losing are very high. But look at the values. When you win, you get a lot. And when you lose a little. So this is one of those games where you have to play it many, many times in order to win a lot of money. The odds of you winning one time are low, but when you do win, you actually win a lot. So the next question makes a lot of sense. If I play this game 685 times, how much would you expect to win or lose? Well, 685 turns times the expected value, or 2.83, is equal to 685, 1938, 55. And I think this is a rounding issue. Yes, this is probably a rounding issue. I will make a point of looking at this and this, noting that the answers are over here and over here. There should have been $3 to make sure that we got that one right when you take your exam. But so I'm pretty sure this is a rounding issue. How would I fix this rounding issue? I would extend these decimals here to make them more precise. This was actually, what's 10 divided by 13? 10 divided by 13 is 0.76. 692. So maybe that's where we had a problem. I will think about this and see where the problem is. Yeah, that's exactly what that was. This is a rounding issue. So this is 3 divided by 13, which gives us 23.2307. And when we do the whole thing and multiply this out, this will actually be $3 even. Okay, so good lesson for both of us. When you're dealing with these decimals, work yourself all the way to 4 decimals when you're doing the probabilities and you end up doing averages, even if the question is asking you to report 2 decimal places. Grab those extra 4 decimals. But that does give us the $3 when you use the 4 decimals, and then 685 times 3 is 2055. Okay. All right. So good clarification. The process is the same, just use more decimals. And now we found ourselves answering the phone again. Just a second. Question 16. A student takes an exam containing 8 true or false questions. If a student randomly guesses on the entire exam, meaning that it is a random probability, what is the expected value of the number of incorrect answers? Or correct answers for that matter, right? Because this is going to be a 50-50. So what is the probability of being incorrect? That is equals to 0.5. How many questions are there? There are 8 questions. And that gives us, if we multiply them together, 4. 4 correct. Or incorrect. This question is asking for incorrect. 4 incorrect answers. Oh, I'm running out of space here. 17. A random variable x is a binomial random variable with n4 and p 0.01. So clearly we're dealing with a binomial question here. What is the standard deviation of x? All right, so this is one of those where I'm going to suggest that you go straight to your cheat sheet. And if you go to your, let me line this up right. And if you go to your book, if you haven't already done this, in the table of contents of your book, at the very back, you have these formula pages, okay? And that brings you to this guy right here, formula pages. So in this case, we're dealing with chapter 5 and 6, and I know I'm dealing with a binomial here, right? And I have a manner of calculating expected value. And up here I have the variance of a binomial random variable. Great. What is this question asking me? What is the standard deviation of x? Well, the standard deviation is nothing more than the square root of the variance. I know it's a binomial, so let me zoom in on this a little bit so that we can get it. So we can get it into the right place. There's the variance. Oh, come on. There it is. The variance of a binomial random variable is np1 minus p. All right. So if the variance is equal to np1 minus p, which is nothing more than the total number of trials, n, times the probability of winning or happening, and this whole thing is the probability of not happening, then all I need to do is take the square root of the variance. Square root of the variance, because I know that's equal to the standard deviation. All right, so what is n? N is 4, p is 0.1, 1 minus p is 0.9, and I'm going to take the square root of the whole thing. All right, so 4, where'd my calculator go? 4 times 0.1 times 0.9 is equal to the square root of 0.36. Oh, how neat. So that gives me, the answer is 0.6 or 0.60 because it's asking you to round to 2 decimal places, 0.60. All right, I don't expect you to have this whole thing memorized. I'm just making a mess here. I don't expect you to have this whole thing memorized. I do expect you to be able to go and find it when you need it. Okay? And let's finish this with number 18. Finally, we have number 18. The number of calls received by an office on Monday morning has a mean of 4. Calculate the probability of getting exactly one call between 8 and 9, which is whatever that is, 8 and 9. Round your answer forward. All right, so this is a Poisson distribution. You're trying to figure out what are the odds of this happening when you know what the mean of it you know what the mean is. Well, with the Poisson distribution, it's very interesting that lambda is equal to the mean here, okay? And our x is going to be equal to that one call. So when we write out the lambda distribution, we write it as the probability that x is going to happen, the one that we're interested in. So we're interested in one call, and that's going to be equal to Euler's number to the negative lambda to the x over x factorial. Now don't let this throw you off, and don't let it confuse you because it's got a bunch of Greek letters. The lambda, just like we said, is the mean. So what's the mean? The mean is 4. So this again is just like plug and play. E is equal to 2.7182 and so forth, and that's a constant. And if we just plug it in, then we have Euler's number to the negative lambda. Lambda is 4. That's our mean. 4 times 4 to the x. What's our x? Our x is 1 over 1 factorial. Okay? So this is going to be 2.71. And many of your calculators will have an Euler's number already programmed into it. To the negative 4 times 4 to the 1, which is 4, divided by 1. So that 1 just kind of disappears. So this is equal to, can I get a little bit more space here? That's not what I want. That's what I want. So this is equal to 2.718 to the, again using that XY button, 4 negative, and that gives me 0.0183, that's a 0, not a 6, times 4 over 1, but I don't need that 1 anymore, it disappears. And I just multiply that by 4, and I get 0.073, again that's a 0, not a 6, 0.732, or 0.733, right, because I'm rounding here. And that's what that is, 0.0733. Okay, so this review is kind of long, but hopefully you get good practice. You got the entire test in front of you. Let me scroll back up to the top. Work the problems. Have as much fun with this as you can possibly have. Lean into the cheat sheets when you can. And remember, you're only going to have 90 minutes during class to have this exam. So make sure you practice before you come in so that you don't run out of time. Good luck.